In this video, we're going to discuss sections 6.4 and 6.5. 6.4 is about assessing normality. The 6.4 homework is largely just going to be a continuation of the 6.3 homework instead of actually covering the stuff that is done in 6.4. However, being able to understand how to assess when something is normally distributed is also very important. Also, I apologize if you hear some noise in the background. One of my neighbors is riding a four-wheeler behind my house. So, the distributions that we've seen up to this point have been assumed to be normally distributed. But how do we determine if something is normally distributed? One way is for us to take a sample and determine if it looks normal. If the sample looks normal, then most likely the population is normal as well. We have some guidelines that we can use to help to make this determination. And these guidelines are: what is the source of the variation in the population? If it's a lot of different factors, each adding or subtracting, then the distribution is probably normal. The histogram should be roughly bell-shaped. As far as outliers go, there should typically not be more than one. We're using the 1.5 times IQR rule to determine whether something is an outlier or not in this case. Keep in mind, these are all kind of rules of thumb. You may have something that is normally distributed and you may end up having two outliers, for instance. These are all just kind of guidelines. These are not set rules per se. And also we have this thing called a normal probability plot or normal quantile plot. This plot is a type of plot that you generate through computer software. And if the points on this lie close to a straight line, then our data is approximately normal. Here we have some steps on how to make a histogram in your TI-83 or TI-84. This is slightly more difficult in something like Desmos. I know on Desmos.com you can create a histogram. I haven't been able to get the histograms to look exactly like they do in the calculator, though. If anyone watching this happens to know of a good online resource to use to create histograms, please email me and let me know. We also have some instructions on using box plots to identify outliers. And some instructions on how to generate normal probability plots. I'm just going through these quickly since you can pause the video if you need to follow these directions. Let's look at some examples of these plots and determine whether something is normal or not based on them. Here we have some data. This data is found in your textbook in section 6.4.1, or in section 6.4. This is example number 6.4.1. In Kiama, New South Wales, Australia, there is a blowhole. There is a table of data in your text. And the question is, do the data come from a population that is normally distributed? And the data are times in seconds between eruptions. You would type all of the data into a list. And when you plot the histogram here, we see that this histogram is skewed right, which points to this not being normal already. When we generate the normal quantile plot, or the normal probability plot, we see that this doesn't look like a straight line. And so this is also suspicious. And if we were to check for outliers, we would find that there are 2 outliers. In fact, our plot would look like this for our box plot. So 2 outliers is also suspicious. And because all 3 of these kind of point to this data not being normal, we're going to conclude that this data is likely not normally distributed. In example 6.4.2, we have one way to measure intelligence is with an IQ score. There's a table of data that contains 50 IQ scores, and our goal is to determine if the sample comes from a population that is normally distributed. When we generate a histogram, we see that this looks approximately bell-shaped. The peak isn't exactly in the middle here, but that's okay. Again, these are not hard and fast rules, and this could just be a quirk of this particular sample. If we took a larger sample or a different sample, we may get data that is skewed the other way, or data that is centered in the middle of this bell curve. The normal quantile plot here looks linear. And if we were to grab the box plot to determine if there are any outliers, it does not appear as though there are any outliers here. And so all of these pieces of data point to this likely being normal. This points to the population likely being normally distributed. Moving on to section 6.5. 6.5 is on sampling distributions and the central limit theorem. First up, we have a couple of definitions. We have a definition of statistical inference. Statistical inference is to make accurate decisions about parameters from statistics. Well, whenever we make accurate decisions here, we want to be able to measure how accurate. And we can measure how accurate using probability. In both binomial and normal distributions, we needed to know that the random variable followed either distribution. We need to know how the statistic is distributed, and then we can find probabilities. So in other words, we need to know about the shape of the sample mean, or whatever statistic you want to make a decision about. So how is the statistic distributed? This is answered with a sampling distribution. Suppose you have a random variable that has a population mean mu and a population standard deviation sigma. If a sample of size n is taken, then the sample mean x bar has a mean mu x bar is equal to mu and sample standard deviation, or rather a standard deviation of sigma sub x bar is equal to sigma divided by square root of n. So here we're looking at the way in which the sample mean is distributed. So the standard deviation of x bar is always going to be lower, because by taking the mean, we're averaging out the extreme values, which makes the distribution of the original random variable spread out. This tells us about the center and the variability of x bar, of the sample mean. Our next thing tells us about the shape of the distribution of x bar. Now we're hoping that it's going to be normal because we know how to find probabilities using our normal curve. And in fact, if the random variable has a normal distribution, then the sample means will also be normally distributed. If the random variable has any distribution, then the distribution of x bar will become normally distributed as the sample size increases. How large does n have to be? This depends on the shape of the original distribution, but around 30, the sampling distribution gets pretty close to normal. The sample size may have to be much larger if the original random variable is really skewed. And we're going to look at an example here. The birth weight of boy babies of European descent who were delivered at 40 weeks is normally distributed with a mean of 3,687.6 grams with a standard deviation of 410.5 grams. Suppose there were 9 European descent boy babies born on a given day and the mean birth weight is calculated. First of all, we want to state the random variable. The random variable here is, of course, x is the birth weight of boy babies here. What is the mean of the sample mean? The mean of the sample mean is just going to be the mean. In this case, it's 3,687.6 grams. This was from our definition of sampling distribution here. Mu sub x bar is equal to mu. What is the standard deviation of the sample mean? In this case, sigma sub x bar is sigma divided by the square root of n. So in this case, the standard deviation of the sample mean is going to be the standard deviation that we have divided by the square root of 9, because we're looking at 9 boy babies. I'm not sure how to type a radical here. There's probably an equation editor. Let's see. I think up here, yep, there is. Let's see, I need something really simple. Where's my simple stuff at? square root of 9. There we go. Kind of messed some stuff up here when I did that. Let me undo this. We're just going to leave it like that. This is standing in for square root. This is 410.5 divided by 3. And we type this into a calculator. This is 136.8 grams, I believe. Let's see. 110.5 divided by 3. Again, this is because the standard deviation of the sample mean is the standard deviation divided by the square root of the sample size. And the sample size was 9 in this case. There were 9 boy babies born. What distribution is the sample mean distributed as? Let's see. In this case, we're told that the original random variable is normally distributed. Because the original random variable is normally distributed, this means that the sample mean is normally distributed. For these last two, we're just going to have to use some of the stuff that we've already done. There's nothing new in these last two problems. Find the probability that the mean weight of the 9 boy babies born was less than 3,500.4 grams. I guess there is going to be a slight difference here. In this case, this is a normal CDF problem. We want the probability that the mean weight of these babies was less than 3,500.4 grams. This means 3,500.4 grams is our upper limit. We're not given a lower limit, so we have negative 1e99 as our lower limit, 3,500.4 as our upper limit. Now we have to be careful here. We want the mean to be the mean of the sample mean, which is actually the same as the mean, 3687.6. And the standard deviation should be the standard deviation of the sample mean. It should be the thing that we calculated above here, where we're asked what is the standard deviation of the sample mean. We should type 136.8 because we're being asked about the mean weight here. And we'll type all of this in. Oh, I have a syntax issue somewhere. Oh, I did not insert a comma. There we go. And we have about 8.5%. So our probability is 0.0856. About 8.56% or about 8.6%. And for find the probability that the mean weight of the 9 babies born was less than 3,452.5 grams. This is a very similar problem, right? I didn't type out what the probability is here, but this is the probability that x is less than 3452.5. This is another normal CDF problem. We're once again given an upper limit and not a lower limit. So our lower limit is negative 1e99. Our upper limit is going to be the 3452.5. Our mean is going to be the mean of the sample mean, which is just the mean. And our standard deviation, because we're being asked about a probability about a mean, we want to use the standard deviation of the sample mean again, which is 136.8. Three, 4, 5, 2.5, 3, 6, 8, 7.6, and win 36.8. And we get 0.0428. So about a 4.3% chance. And this is everything for sections 6.4 and 6.5.